Hello everyone. This video covers sections 2.5 to 2.7 from the textbook. So we're going to start with section 2.5, which is called the sample point method. And this is just a continuation of section 2.4. Remember, in section 2.4, just recall this, because this is the basis to everything we're going to do right now. Recall from section 2.4, you have an experiment. So once you define what the experiment is, you find the sample space. And once you have a sample space, then you technically can find any probability depending on which event you want based on the sample space. So this is just a modification of section 2.4, and it is called the sample point method, but it's essentially the same as section 2.4. So let's do one example. So the example says the following. You have 4 equally qualified people that apply for two identical positions. One and only one of the applicants is a member of a minority. So the positions are filled by choosing 2 applicants are random. So what are all the possible outcomes for this experiment? So for part A, let's say the A1 means the first applicant, A2 is the second applicant, A3 is the third applicant. And we're going to use N for the minority applicant. So you have 2 people. So, 4 people. So therefore, all the possible outcomes are this. So therefore, the possible outcomes, which is, remember, the sample space. Without the sample space, you cannot find any probabilities. So you need to be sure you have this. So you could have A1, A2, that's one outcome. It could be A1, A3, that's another one, or A1 and M. Or it could be A2, A3, or it could be A2, M, or it could be A3, M. So in total, you have 6 outcomes. Right, so therefore, a reasonable probability should be 1 over 6, assuming that all of them are equally likely. So that would be a reasonable probability. Now, part C says find the probability that the applicant from the minority group is selected. So the probability that the minority will be selected. Remember that you had to pick 2 people at random, so that will be the case if you have this one. Minority will be this, and this, which is 3 of them. So the probability will be 3 out of 6, or 0.5, which is not bad. 50% is pretty good. All right, so as you can see, section 2.4, 2.5 are essentially the same. They just have different names. So by now you have realized that the sample space is very, very important, and that's sometimes the tricky part to determine. So now in section 2.6, which is what we're going to do next, they have 3 methods to be able to count how many outcomes you have in a faster way. But the idea of finding probabilities is still going to be the same. You have the sample space, how many sample points you have in the event you want, you divide, and you're done. All right, so let's go to 2.6, tools for counting sample points. The first tool is going to be called the multiplication rule. And just like the name suggests, you're just going to multiply. So the multiplication rule says the following. Given you have n elements, a1 to am, and n elements, b1 to bn, it is possible to form m times n, the multiplication pairs, containing one element of each group. We kind of did this already. You remember one of the examples we have when somebody has 3 kids. You have total 8 choices, and the reason was the following. You have 2 choices for the first one, 2 for the second one, and 2 for the third one. So by the multiplication rule, you have 8. Now, the only disadvantage of this rule is that it does tell you how many sample points you have, but it doesn't tell you what the sample points are. But sometimes this is all you need to know to find the probability, okay? So again, this is good because it tells you how many you have, but it doesn't tell you what the points are. You will still need to figure them out, but at least you already know you have 8. All right, so let's use this principle to see how many different passwords you can have for an iPhone. So iPhones now, the password consists of six digits. Okay, 5, 6. So remember, for a password you can repeat. So this is called with replacement, which means you can use the same number over and over. So you have 10 choices for the first one, 10 for the second one, 10 for the third one, and so forth. So therefore this will be 10 to the 6. That's how many choices you have. So therefore the probability that you will get the correct password on the first try, it will be 1 over 10 to the 6. Now, if you cannot use the same number of values again, meaning you cannot repeat it, then it's called without replacement. Like, let's say that once you use the number 4, you cannot use it again. Then the next one will be 9, then will be 8, 7, and so forth. And we'll do an example of that in a little bit. All right, let's look to another example. Let's say you toss a die 3 times. How many sample points are there? So we're going to do exactly the same thing we did right now. You have 6 choices for the first one, 6 for the second one, 6 for the third one, so this will be 6Q. So these are the total number of sample points, okay? Which is essentially the same thing for this one too. All right, so let's say that A is the event that the sum of the digits when you roll the 3 dice is equals to 3. So you notice there is only one way to get 3. You get a 1 on the first one, 1 on the second one, and 1 on the third one. So therefore the probability of getting a sum of 3 will be 1 over 6Q. Okay. Now if A is the probability that the sum is 4, so next we need to figure out all the different ways or all the sample points that gives you a sum of 4. So this will give you a sum of 3. So if you want a sum of 4, you could get that by, if the first one is a 1, the second one is a 1, and the third one is a 2, the sum is 4. Or if the first one is a 1, the second one is a 2, and then a 1, that also gives you 4. Or this could be 2, 1, 1, that also gives you 4. Technically, you have 3 outcomes. So therefore, the probability for this one, we call this B instead. So therefore, the probability for B will be 3 over 6Q. Okay, now let's do a slightly different example, but same idea. Let's say you have a 100-meter race, and you have five runners, and assuming there is no ties, and how many ways can the race end? So somebody has to get the first place, then somebody has to get the second place, third place, fourth place, and then the clippers on the last place. So only one person can get the first place, but any of the 5 can be the first place. So therefore you have 5 choices for the first one, then 4 for the second one, 3, 2, and 1. So technically this is 5 factorial or 120. So remember recall, because we're going to use this many times, the factorial, that by definition n factorial is equals to n times n minus 1, n minus 2, all the way to 2 times 1, and 0 factorial is equals to 1. Okay. So therefore there is 120 different ways to finish the race. So if you buy a ticket guessing the order of the races, then your chance of predicting it will be 1 over 120. Okay, now let's look to the following definition, which says the following. An ordered arrangement of R distinct objects is called a permutation. Okay? So now we're going to deal with permutations. So the number of ways of ordering n distinct objects taken R at a time will be defined by the symbol n to the PR. There are many ways to write this. Most books have it like this, NPR, or sometimes it's like this, but we'll just go with the notation that the book has, which is NPR. Okay? Now you can get this easily by the extension of the multiplication theorem that we just did right now. So in essence, P and R, or PRN, is going to be equals to n factorial, which we talked about the factorial already. And it will be n minus R factorial. So that's the formula. Now the reasoning for the formula, so reasoning is the following. You have n choices for the first one, then n minus 1 for the second one, n minus 2 for the third one, and then for the R one it will be n minus R plus 1. Now if you modify this by multiplying by 1 in here, it will give you this. So this one looks nicer, but this is essentially this thing right here. And you should check this by yourselves, that this simplifies to this. Now permutations are used when order is important, and by order here means the selection, ordering, like how things are selected. So if you select 3 people, whoever gets selected first gets something different than whoever gets selected second or third one. For example, let's look to the following. It says this semester a particular matrix 80 has 30 students, so therefore n is equals to 30. The professor will choose 3 students randomly. The first student selected will receive an A. The second student selected will receive a B, and the third one will receive a C. So the point is how many, so the question should be here, how many sample points are there? So how many sample points are there, which is technically what is the sample space. Well, here, since we're selecting 3, R will be 3. So therefore this will be P 30 of 3, which will be 30 factorial over 27 factorial. Or this will be 30 times 29 times 28 times 27 factorial. You can also use a calculator if you don't want to go through this. And then the answer is 24,360 or 24,360. So therefore there are 24,360 different ways to select 3 people from 30 if the order is important, meaning the first one will get an A, second will get a B, and third one will get a C. Let's say that you have 3 students in the class, so say you have these 3 students. I'll say you have Pedro, Kid, and Raul. So the probability that Pedro will get an A, Kid will get a B, and Raul will get a C, it will be 1 over this. The probability that Kid will get an A, Raul will get a B, and Pedro the C is also 1 over this. Okay? Alright, so now let's look to the following definition, which is highly related to the previous one. So the definition says the following: the number of combinations, okay, of n objects taken at a time is the number of subsets, each of size r, that can be formed from n objects. And this will be denoted by c to the nr, which is sometimes just called n choose r. And the notation, I believe the book uses this too. Okay? So the definition is the following: is n factorial, and then will be r factorial, n minus r factorial. Now for combination, the selection order is not important, which means if you select 3 people from 30, all of them will get the same thing. In our case, that means that all of them will get an A, or all of them will get a B, or all of them will get a C. Right? And also, you don't want to compute this by hand. If you have a scientific calculator, it can do it for you. So let's compare the amount you get from here compared to this one using the same numbers. So here, let's say you have 30 people and you want to select 3 students, and each of them will get an A, for example. So then it will be 30 factorial over 3 factorial times 27 factorial. We calculated this part already. Remember, this was 24,360, and on the bottom you have 3 factorial. Remember that 3 factorial is 6, so you divide, you get the following: 4,060, which you can see is much less. So therefore, if the order is not important, this number of sample points is much smaller than when the order is important. We did this example at the beginning of the video, but now we're gonna do it with combinations. So first, let's look to the sample space. Remember that the sample space had 6 sample points. So in our case, our sample space is gonna be in how many ways can you select 4 from 2? I mean, how many ways can you select 2 from 4? So since this is a combination, this will be 4 factorial over 2 factorial times 2 factorial, and you should check that this is equal to 6. Now let A be the event that the applicant or the minority applicant is selected. Minority applicant is selected. Again, this is exactly the same question we did at the beginning. Okay? So we need to find how many sample points are in this event, and for this we're going to use the multiplication property. So you have technically 3 people that are not a minority. So remember, this was A1, A2, A3, the 3 people, and you want to select 1 times, that's where the multiplication principle comes in. You have 1 minority person, and you want to select 1. So this is the minority. Now this one is going to be 3 factorial over 1 factorial times 2 factorial, and this just will be 1 factorial over 1 factorial times 0 factorial. You can check that this is equals to 1 and this is equals to 2. So therefore the probability of A is going to be 3 over 6, which is exactly the same thing. Or you can leave it in combinations if you want to. The probability of A, it technically will be C31 times C11, and this will be C42. I wrote this using different notation. This is technically correct, but let me write it the way the book does it. The book is writing it like this, but most places will write it like this. Okay. All right, so let's go to the last section, which is section 2.7. This is called conditional probability and independence. So let's start with the definition of conditional probability. The definition is the following. The conditional probability of event A, which is this, it should be event A, given that B has occurred, is the following. So essentially what this means is, what's the probability that A is going to happen given that B already happened? And the definition is just the intersection divided by what you already know that this is given. And this obviously assumes that the probability of B has to be positive, cannot be 0. Okay? All right, let's look to an example here, which says the following. The XYZ association has 100 members. 25 of those members are Mexican, 32 are Catholic, and 8 are both. Like I said before, you don't have to draw Venn diagrams, but they will make life pretty easy for you. You will see. So here you have a Mexican or Catholic, and both are A, and you have 27 that are Mexican, so therefore this has to be 17, and the other one is 24. And therefore outside you have 51. So now notice that this is already telling you the following. So this is what you already know. You already know the probability that somebody is Mexican is 25 over 100, so that's given. Or the probability that somebody is Catholic is at 32 over 100. And also the probability that somebody is Mexican and Catholic is A over 100. Okay, so this is the given information. That's how I create the graph. But part A is asking if the randomly selected person is Mexican. So you already know that the person is Mexican. So given that the person is Mexican, what is the probability that the person is also Catholic? Okay, so that's what it's asking. That's different than just asking you what's the probability that the person is Catholic. Okay, so then this will be, in this case, the probability of being Catholic and Mexican divided by the probability that the person is Mexican. So therefore this will be 8 over 100 divided by Mexican, which is 25 over 100, which is A over 25. Now let's say that part B, there was a part B, and the question was this. What's the probability that the person will be Mexican given that the person is not Catholic? So then this will be all the people that are Mexican but are not Catholic divided by all the Catholic people. Now, we did this before, so remember, Mexican and not Catholic is this part. These are the people that are Mexican but are not Catholic. So on the top, this will be 17 over 100. And on the bottom, it will be all the people that are not Catholic. Well, you have 32 people that are Catholic. So these people are not Catholic, and these one are not Catholic, which total is 68. So it will be 68 over 100. So therefore the answer will be 17 over 68. All right, so let's try the next example, which is very similar to the first one, except that it's in decimals instead of whole numbers, but it's essentially the same thing. So let's do the Venn diagram. So let's say this is R and this is C. Now to have some context so that it makes a little more sense, let's say that R means Republican and C means Christian. So you have 10% that are Republican and Christian, so this will be 0.4, this will be 0.3. So this is 5A, so outside we'll have 0.2 to have 100%. So therefore, if I ask you what's the probability that the person will be Republican given that you know that the person is Christian, this will be Republican and Christian divided by all the people that are Christian. So in our case, this will be 0.1 divided by 0.4, it will be 0.25. Okay, part B, let's say the question is this: what's the probability that the person is not Republican given that the person was Catholic? So then this will be not Republican and Catholic divided by the probability the person is Catholic. Remember, Catholic already say was 0.4. Now on the top says Catholic but not Republican, which will be this. And this will be 0.3. So the answer is 0.75. You can also find interesting probabilities like this. What's the probability that the person is not Catholic given that the person is Republican and Catholic? And using the formula, this should be not Catholic and Republican and Catholic divided by R and C. Now the bottom is 0.1, but notice on the top, R and C is this par. If you do the intersection with the complement, there's no intersection, so the answer is 0 for that part, so it will be 0. So the answer will be 0. So it's impossible to get to this part. All right, let's try another example, a slightly different version. So here you have 310 students, college students. So before we find the conditional probabilities, if I ask you what's the probability that somebody is Democrat, well, clearly that will be 115 over 310. If I say what's the probability that somebody is Muslim, so that will be 95 over 310, and so forth. If I ask you what the probability that somebody is not a member of the Green Party, then will be 200 over 310. Now, if the question is, what's the probability that somebody is Democrat given that you know that the person is already Muslim? So using the conditional formula, this will be Democrat and Muslim divided by the probability the person is Muslim. Now, Muslim, we already say it was 95 over 310. And now, Democrat and Muslim is this value right here, which is 45. So this will be 45 over 310. So this will cancel. So the answer will be 45 over 95. Yeah, that's it. All right, so let's say that we're going to find this now. What's the probability that somebody is going to be Christian given that you know that the person is not a member of the Green Party? So therefore, this will be all the people that are Christian but not members of the Green Party divided by all the members or all the non-members of the Green Party. We already found this one. This was 200 over 310. And on the top, you have, so these people are Christian, but you don't want any members from the Green Party. So you have to use this value, which will be 90. So it will be 90 over 310. So the answer will be 90 over 310. All right, so finally, the last concept that we will be looking into is the concept of independence, which is completely related to conditional probability. You'll see right now. So two events A and B are to be independent if any of the following three holds. So notice this part says A and B are independent if the probability that A is going to happen, given that already B happened, is going to be A, meaning that B doesn't affect A at all, so that's why they are independent. Now, the most common way to check for independence for most books is usually this formula, in which says that if two events are independent, then the probability of the intersection is equal to the product of the probabilities. So, for example, if I tell you that the probability that A is equal to 0.4 and the probability of B is equal to 0.3, and the probability of A and B is equal to 0.14, since the probability of A times the probability of B is equal to 0.4 times 0.3, which is equal to 0.12, and this doesn't equal to A and B, then this implies that A and B are dependent, not independent. Okay, so it's as easy as just checking if this is the case. Or you can go with the conditional probabilities, like we will do in the next example. Now, we did this example at the beginning on this of section 2.7, and remember from there we knew that the probability that somebody is Mexican was 25 over 100. The probability that somebody was Catholic was 32 over 100, and the probability of somebody being Mexican and Catholic was 8 over 100. So there are two ways to check if they are independent. So let's go with this part first. So notice here that if you multiply this 25 over 100 times 32 over 100, the question is, does this equals to A over 100? So now if we use just fraction simplification, remember this is 25 times 4, this is 8 times 4, so you can see that you end up with A over 100. So therefore, yes, they're independent. Okay. Now from the very beginning of this section, we found this. So this is another way to show that it's independent. Remember the probability that M happened, given that C already happened, was equals to this. Okay. This was A over 100, and this was equals to 32 over 100, which is equals to A over 32. But A over 32 is the same thing as 25 over 100, which is the probability of M. So therefore they are independent. Remember, this is 0.25, and this is also 0.25. So that's another way to check. Right, let's do another example here. The problem says the following: and a standard deck of cards has 52 cards, of which 26 are red and 26 are black. The deck contains 12 face cards, and the question is the following: are the events red card and face card independent? Okay. So here R is going to mean a red card, and F a face card. Okay. So now to check if they're independent, all we have to do is this: is the probability of R and F equals to the probability of R times the probability of F. If this is the case, then they're independent. If this is another case, then they're independent. The problem already tells you that 26 are red, so it will be 12 over 52. And face cards is 12 over 52. Now, since there are 12 face cards, and half had to be red and half had to be black, the probability that a face card is red is going to be 6 over 52. And you can check again by simplifying fractions. This will give you 2 and this will give you 6. You have 6 over 52, which is equal to 6 over 52. So therefore that means that they are independent. Okay, so let's say this is part A. Now if we do part B, let's add another event. Let's say the H stands for a heart. And if you are not familiar with cars, don't worry, you will not have any cars problems on the exam, but they are good for illustration purposes. So let's say you have a heart and there is 13 of them. Okay. So the question is the following: are hearts and red cars independent? So is the probability of R and H equals to the probability of R times the probability of H. Now, red, what I say was 26 over 52, and H, there is 13 hearts. Now, all the hearts are red, so therefore this will be 13 over 52. And notice right away that this cannot be the same, so therefore these are not independent. And the reason why is because all the hearts are red. So these two events are independent, but these two, this and R, are not. Okay. Now let's refer back to the example we did with the table that we have Muslim, Catholic, Muslim, Christian, other, Green Party, Democrats, and so forth. So one of the questions that you had to do there was this. So recall the question was this: the probability that somebody will be Democrat given that the person is Muslim. The answer we found was 45 over 95. Now, this is not equal to the probability of being Democrat, which was 115 over 310. So therefore that implies that Democrats and Muslim are not independent events. Or you can say they are dependent. Okay. Now, the opposite with independence is actually a very powerful thing, and it's going to be very, very important in the class. And when I say the opposite, I mean this. If you know the two events are independent, that makes finding probabilities pretty easily. So to check for independence, you have to either do this or this part. But if you already know that events are independent, that makes finding probability very easy. So independence is actually one of the best friends you can have. For example, let's say that a family has 10 kids, okay? If you want to find the sample space based on what we did at the beginning, or by the multiplication principle, the sample space, it will be 2 to the 10 power, which is equals to 1024. So that's a lot of points. You want to check all of them. So now let's say that you are interested in the event of, let's say A is the having at least one boy. Okay, so that's what you want to get. So to do this directly, it will take you a long time. So instead we go with the complement. The complement will be no boys, which means all girls. Okay. So all girls means that the first kid was a girl, and the second one was a girl, and the third one, and so forth. Okay. So therefore, by independence, the probability of the complement is going to be the probability of G1 times the probability of G2 all the way to the probability of G10, which will just be 1/2 to the 10 power. So therefore, the probability of A it will be 1 minus the complement, which will be this. And you can see this is pretty easy to compute now. So this will be 1 minus 1 over 1024, which is 1023 over 1024. If it wasn't because of independence, then this problem would have been very, very, very long. But independence, you can see, made the problem pretty easily. And that's it.